Okay, so this video we're going to talk about using the Bootstrap. Uh, Hello to the person who just joined the stream. If you're watching this recording, this is also streamed. Feel free to join us for future live sessions. Okay, so we want to talk about the Bootstrap. And the Bootstrap is a very general method in statistics, and we're going to introduce it here, not because it's going to be something we use a lot, but the general idea of resampling is something that we're going to use a lot. And later on in a method that we introduce, it's going to internally use a bit of bootstrapping. So while we won't sort of like often, fully and directly use the bootstrap, it's a really nice idea to know about, and it'll help us learn some other things. If you've taken Stat 428, this is going to be, complete review for you. Yeah, so let's have a look. So this is sort of the setup that we introduced when we were talking about simulation. Again, we have a random sample of size n from some population distribution, and that is, denoted by x1 through xn, capital for random variables, and then you have the realized values, either potential or real. And so we have, often we have some parameter of interest, be it an expected value, a variance, a particular probability. Anything that's a function of a distribution could be a parameter. And then we have some estimator, which we often denote theta hat. And then the question we were sort of asking ourselves last time is, well, how do you get the distribution of your estimator? And we didn't really say why last time, but in this video, the reason we're going to want that distribution is because we want to make interval estimates. So we want to know the distribution of theta hat so that we can build essentially a confidence interval for theta. So if theta hat is a point estimator, we want an interval, a range of values where we believe that theta exists. Okay, cool. So in the last video, when we were talking about Monte Carlo simulation, we assumed that we knew the population distribution. But the natural question is, well, what if we don't? Because in practice, you don't know the population distribution. So you might see where we're going with this. So you estimate the population distribution via the single sample that you have. And then you sample from that distribution. So I guess you could call that simulate. So get a single sample from the unknown population, estimate the population distribution, then create follow-up samples. That, in not so many words, is how the Bootstrap works, so we need to talk about that in a lot more detail. So to define sort of two quantities first, we're going to talk about Bootstrap resamples and Bootstrap replicates. So a Bootstrap resample is a sample of size n with replacement, that's the important part, from the original sample. So this is actually the same as what I just said. So this is so this is the same as taking a sample of size n from the empirical distribution. That's a bit of a technical note that it's not super important if you're not aware of that. But essentially, the empirical distribution places probability 1 over n on each data point. So if you sample from that distribution, that's the same as sampling a size n with replacement from that. We'll see that when we get to R. That'll make it clear. So those are called Bootstrap resamples. Now, if you calculate a statistic on one of those things, that's what's called a Bootstrap replicate. So we're going to do that. We're going to create Bootstrap resamples, and then we're going to calculate Bootstrap replicates. It's kind of a simple idea. We need to see it. But what I first want to do is show you visually how this compares to what we did last time. So last time we talked about, simulating data sets. So here we have the sort of schematic I drew last time where we have some known population distribution at the top, and then we repeatedly generate samples of size n from that using something like the rnorm or the rexp function. And then we calculate the statistic, like say the sample median on each of those samples that you generate. The problem being, of course, that we don't know this, so that won't work. So what are we going to do instead? Well, we're gonna do this, which kind of looks like this. And I purposely drew this picture in a very similar way, but there are some subtle and very important difference. Okay, so this is the original sample. So in practice, we're only going to get one of these. So we'll just have this one sample from the population. And in this example, there are 10 observations. So in place of these, fully random samples from the population, what we're going to do is say, okay, well, this sample we have is sort of a reasonable representation of the population. So we're going to sample from these observations with replacement data sets of the same size. So this first sort of row here, these are the Bootstrap replicates. So to get this first one here, we take a sample of size n from the original sample with replacement. So it might not be super easy to see. Oh, I can do that. So, perfect. So notice here that I haven't written out a whole sample of size 10, but notice that x1 appears twice. That's possible because we have sampling with replacement. If I go over to the next one, here x1 does not appear, but x2 appears twice, and like this last one. So generally we say we do B for Bootstrap, B Bootstrap replicates, Bootstrap resamples. Here this one has x1 but not x2 and x3 and so on and so forth. So each observation has some probability of being in the sample, but it could or could not. So we repeat that process B times. And those are called the Bootstrap resamples. And then, so whatever statistic we're interested in, say, the median, so calculate the sample median on each of these Bootstrap replicates, and those would be calculate the statistic on the Bootstrap resamples, and that would be the Bootstrap replicates. So pretty simple idea, but how then do we use this to do something useful? And so while you can do a lot of things with the Bootstrap, the thing that you'll see it used for the most is creating a Bootstrap confidence interval. So there are many ways to do that even. And there's many ways to do the Bootstrap. So we're doing the most basic version. And to create confidence intervals, we're going to use what's called the percentile method. So say I had done this procedure B times for some statistic, and therefore we have B Bootstrap replicates. Okay, well, and then I plot a histogram of them. And so I want to create, let's say, a 90% confidence interval. Okay, so what I want is two values. a lower and upper bound such that 5% of the observations, 5% of those Bootstrap replicates are here, 5% are here, and 90% are here. And so that is actually really easy to do in R with the Quantile function. So since this method is sort of so computationally based, we're gonna, go ahead, get into R and have a look. These are my notes about what examples to do. Okay, so switching over to R now. How do I do that? Like this. Okay, cool. But I need this. Okay, so right. Let's say we want to do an example where, well, let's just say this is the data that we have. So we have these 16 observations, and now we're sort of living in a world where we don't know this. I mean, we know it because it's right in front of us, but we're going to pretend that we don't have this information and say, okay, let's say we wanted to create, let's write it down. Bootstrap confidence interval. Let's do a 95% confidence interval for the median, right? So what we want to do is, okay, so we're going to estimate the true median with the sample median. And so we want to generate a bunch of Bootstrap replicates of the sample median, and then sort of look at, the right quantiles to get that Bootstrap confidence interval. Okay, so I'm actually going to do this a couple of ways. Well, I guess I'll do it one way here, and I'll do it a different way here. But note that there are a lot of ways to accomplish Bootstrap resampling, especially in R. You might notice that there's a package called boot, and that I'm not using it. That's not because there's anything wrong with that package. It's just that I think that there's so much going on in that package, it confuses what's happening when we can do it a lot simpler here. Okay, so we have this data here, right? And I want to be able to create these Bootstrap resamples. This is actually incredibly easy to do. Just use the sample function. That might be hard to see here, so let's do a different example real quick. So if I take a vector from 1 to 10, so that's just the numbers 1 through 10, and instead I call the sample function on it, notice that, oh wait, sorry, it's good that I did this. So notice that this is just rearranging, but they all the numbers always appear once. That's because by default, replace is false. We can verify that. If I could type. I want it from here. So replace by default is false. You can't see this. Still getting used to some of this. Webcam. So replace by default is false. Okay. So what I need to do here is do true. So now, okay, so here's a great example. I took a sample, and by default it uses the same size, so that's good. But notice how this is an odd sample, 4 7s, and I think 2 does not appear. And so we can repeatedly do this. So basically every time I run this, that's a Bootstrap resample. Okay. So if I go a step further, well now let's return to the original example. Except I need to do this. Okay, so these are now Bootstrap resamples of that single sample that I took. So it's always, values from within here, but some appear more than once, some don't appear at all. Okay, so then I want to calculate the median. Cool. So this is a single Bootstrap replicate. So again, here we create the Bootstrap resample, and then we immediately calculate the Bootstrap replicate, that is, calculate the sample statistic that we care about. Okay, so if I continually run that, these are Bootstrap replicates. And so then what I want to do is, well, do this a bunch of times. So that's where the replicate function comes in handy. Generally, you want to use a really big value. I think 5,000 is probably good. Need to get rid of this. Let's store this. So we'll call this boot medians. Okay. Let's have a look. Looks good. Let's have a look at the distribution then. Okay, it's got some weird spikes, and that's going to happen because we only have so many observations. If we had a bigger sample size here, this would be smoother. You might think that it'll smooth out if we do more here, and it will a little bit, or maybe not. But essentially, there's only so many Bootstrap replicates that can exist here, given that there's only 16 observations. Like, we're exhausting all the possibilities. So that's a funny looking distribution, but that's okay. We can continue on. This might not be the best, but it'll work. So we want a 95% confidence interval, right? So I'm going to use the Quantile function. I'm going to, so the X is going to be the boot medians, and the probabilities are going to be, so let's see, I need 0.025 to the left and 0.975, something like that. So this would be a 95% Bootstrap confidence interval. Let's try to visualize this. Let's clean this up a bit. Let's put a box around this. Now let's do app line v equals this. Color pink, and let's do okay. So this is a visual representation then of the confidence interval. There's 95% of the observations, or 95% of the Bootstrap replicates are between this number and this number. So that's how we do that. So I'm going to redo this real quick with a bigger sample size here. Let's do like 75. So this is now our original sample, calculating the Bootstrap resamples. And so that's a much nicer looking plot. You don't see these weird spikes. And we see very different median here because we're observing more observations. So we're seeing more of the right tail there. That's not unusual, but okay, so that's how you would do that. But basically, pick your poison. Calculate whatever statistic you want on there, and then repeat the procedure. Calculate a confidence interval like this. Okay, so let's do. So one thing that hasn't happened yet is I haven't verified in any way that this is something that works. So something we might come back to down here is saying, well, if this procedure works, I should be able to start here and run from here down to here repeatedly. And 95% of the time, the true value of the median should fall in here. I can't. I said it, now I have to do it. Okay. So let's think about what we need to do here. We need to first generate sample. So we're gonna this is gonna be like a few meta levels here. So we're gonna generate a sample from the known distribution. Then we're gonna do the whole Bootstrap procedure. So we'll say do Bootstrap resample replicates calculate CI, and then check if true median is in interval. Okay, let's do it. So we're going to do this for this median example. So the first thing I need to do is this. Okay, cool. So that's generating data. Let's do 50. Just because the more observations, the more computing power. And I haven't dropped a frame yet, but we'll see what happens when I do a bunch more. Okay, so then I want to do this. So that's so far we've done this. Then we're gonna do this. So that's this part here. Oh, sorry, that's just this part. Then we'll do. So we'll call this the boot CI is here. Okay, so I'm just gonna check this real quick. So there's the data. There's the Bootstrap replicates. There's the CI. So I need to calculate the true median real quick. So if we do QEXP and give it a P of 0.5 for the median and a rate of 0.5, so that's the true median. We're going to need that. And then so I want to say, okay, is the true median greater than the lower bound? It is in this case. And is the true median less than the upper bound, which would be the second point here? It is. And then are those both simultaneously true? Okay. Cool. So okay. So basically what I want to do now is repeat this whole process. That's repeating Bootstrap resampling. So that's a lot of repeating. So I'm going to write this as a function now to make my life easier. Check if in interval. Interval is a function. It's not going to take any arguments. It's just going to repeatedly do this. So if I run that function, it just comes back with either true or false. And because this is going to annoy me, I'm going to do this. Okay. So it's just going to return true or false. And what we would hope is that it is true more than 95% of the time. I say more than because if it's less than, it's just an invalid interval. So our first hope is that it's above 95%, and our second hope is that it's as close as possible to 95%. Our third hope is that this doesn't blow up my computer when I do it. So what we're going to do is we're going to replicate. We're going to start with just 100, that process. We're going to call this in interval. So what we're doing here is we're calculating 10,000 Bootstrap replicates 100 times. What's 10,000 times 100? That's how many data sets we're generating. So this is taking a while. So to do this right, I would need to make this number pretty big, but we can see that this is not going too well here. I would note that, well, we'll come back and do something real quick too. So I should have been smart and timed how long it takes to do this once and then adjust it accordingly. But I really need at minimum 100 here, or else the whole thing is for nothing. So while that's running, I'm going to start to do some other stuff. So you might be familiar with the syst.time function, but that is sort of not the easiest thing to work with. Instead, I would recommend... Oh, do I not have it installed? Okay. So, so there's this package called micro benchmark. It'll be a much better tool for doing system timings, and whoa, I don't want to run this until this is done running, so now I'm really behind. Okay, it ran. Okay, so we see like, oh, the true meeting was in the interval all these times, but not this time, etc. So how about we look at the mean of in interval? All right, success. So it was higher than the stated level, so that's good. Is it a little high? Yeah, but that's fine. But also, we don't know what it really is because we only did this 100 times. We should do this a bunch more. But hey, so I'm satisfied. That's good. But now let's do this. Okay. So what I want to do is... Oh, I should load the library or package. Okay, and then use this micro benchmark and then say, I want to do it on this function and I want to do times, let's say 2. So this did some timings, right? So I forget what the nanoseconds. So of the 2 times we did it, on average, it took 74 nanoseconds. I don't know how long a nanosecond is, but if you ever need to do system timings, consider this function from this package. Okay, so that was fun. Let's consider a real world example. So okay, so a couple notes here. So I didn't load the tidyverse package like I normally do, and I didn't coerce this to be a tibble. But if you're working inside of R Markdown and you have like the newest version of R Markdown or the newest version of R Studio, if you sort of output a data frame or a tibble, it does this nice viewer thing for you. So this is data on melanomas, which is a type of skin cancer. Sorry, I'm not a doctor. It's a type of cancer, mostly on the skin. I think you can also have a melanoma like on your brain, but I'm not a doctor. So let's look at the documentation here. So I need to get rid of me and the keyboard for a second. Okay, so this data set is about how long people with malignant melanoma, so cancerous tumors, live. So this time variable is the survival time in days. So yeah. And it's saying that it's possibly censored here, but in the interest of we don't want to introduce the concepts around censoring, we're just going to assume that this time variable is literally, okay, so you got diagnosed with a malignant melanoma. How long do you survive? Okay, cool. So what we want to do is ask the question, what is the probability that you live longer than, let's say, 5 years with a malignant, did I spell that right? Sure. Melanoma. Okay. So, the first thing we would do is say, well, let's look at, let's actually, that's the documentation. Let's store this as, just store it as mel so we can access it quickly. So first let's look at that time variable. There's the times. They see this data set seems to be ordered by time. That's not a problem. Let's take a quick look at the data. Okay. So notice that this is in days. So to go to years, we would divide by 365. So, you know, at first glance, the probability that you survive longer than 5 years is sort of like, you know, the area to the right of 5 in this histogram. Another way to look at that is so it looks like in that initial data set, 60% of the folks in there lived longer than 5 years with the malignant melanoma. I don't know how that fares against other cancers, but not the best odds. But so, this was just one sample. So we assume that there's some variability in this statistic here. So what we really want to know is what's the true probability that someone lives longer than 5 years. So what we'd really want is let's say we want a 99% confidence interval, because there's some variability. Like maybe it's more like somewhere in a range of 40 to 80, and that's like, well, man, then you just really don't even know. So let's do a confidence interval, and let's also realize a few things here. So we're doing this as an example of doing the bootstrap, but realize that we're sort of making some gross statistical errors. One is we're ignoring this censoring, and two, we should be careful to say that this would only apply to, say, cancer patients in Denmark, given where this data came from. And really, we'd like to know more about where this data came from. Like, did it come from multiple hospitals? How, was it randomly sampled somehow? Like, we're assuming a lot about the data, that it's a nice random sample. But so we'll just say that this analysis is valid for Danes, or people from Denmark called Danes. That's who this is going to work for. Okay. So I'm going to do this in a pretty roundabout way, because I want to use per from the tidyverse, and I want to store a lot of intermediate steps to, one, show how per works, and two, sort of show how Bootstrap resampling works. So I'm going to need the per package. Okay. So it should be pretty obvious, or I don't want to say that. Like, I could go straight to Bootstrap resamples, but I'm going to do an intermediate step from there even. So here's what I'm going to do. So first, we only care about this time variable. So I'm going to extract it from the data set, and that's something I normally like doing, but so this is sort of the data that we're working with. Okay. So there's 205 observations. So think about what this does. So let's say I sample 205, but I want to do replace is true. Does that work? Okay. So what do I have here? So you could think of this as, okay, so this is instructions on what rows to take from the original data set to create a Bootstrap resample. Meaning, if I did time like this, I guess it wouldn't be rows anymore, it'd be observations, because we're just working with a vector. But so these are creating Bootstrap resamples. But so what I'm going to do is I want to store a bunch of these. So I'm going to do something a little bit funny. Let's just do 100 for the sake of... so let's see, we'll call this boot index. Okay, so I ran some code. Let's see what it did. Who knows? Maybe I got it wrong. Oh no, it's outputting so much stuff. 100 was even too many. Okay, so it's a list, and each list has a vector of length 205. And what are these numbers? Well, they're telling you which observations to put into a Bootstrap resample, right? So, like, we're saying that the first Bootstrap resample will have observation 51, 205, 154, and so on and so forth. Okay, so now what I'm going to do is this. And I could get this wrong along the way, so bear with me. Oh, sorry. One thing I'm going to say is part of the reason I'm doing it this way is because on the quizzes, you're going to be given a list like this. That way, it'll make the randomization easier to control. Okay, so I want to now make the Bootstrap resamples. So I'm going to make a function called make boot resample. And it's going to be a function of a data set, or in this case, a data vector, and an index. So essentially what you're going to do is you're going to take the data set and subset it by the index, and that's all it's going to do. So for example, if we took the boot, the first one of these things, right, and did time, so that would be the first Bootstrap resample. But we want to do that for everything. So what do? We want to map to the boot indexes this make boot resample function. And we want the data to be time. And so this should be the boot resamples. Did I get it right? Who knows? Let's find out. Nope. Okay, so notice that there's a function stored, because I didn't run the function. I sort of returned the function. Data's missing. Oh, I guess I can just do it like this. Aha. Yeah, this is what I need to do. And then say index is .x. Okay. Okay, cool. There we go. I might do another video specifically on map and per. I forget which video I did it in previously, but refer back to that one for now, but I might make a separate one there. Okay, but so first Bootstrap resample, second Bootstrap resample, third Bootstrap resample, and so on and so forth. Okay, cool. So we have the indexes, we have the resamples, now we want the replicates. So we're going to map to this. Let's make a function in place that says the mean of, the resample greater than 5 times 365. 365. And these will be the boot replicates. Okay. So essentially what we're saying is, each of the Bootstrap resamples, put it right here. Wait, that shouldn't be okay. Put it right here. Compare each, element within there to this quantity here, which signifies 5 years. Take the proportion of those. Hey, that looked like it worked, except it did a list. In this case, we'd probably just want a vector, so we do this. Cool. There we go. And again, we only did 100 of these. We should probably do a lot more. But we said way back when we wanted a 99% confidence interval. So, quantile of the Bootstrap replicates. We want probability. So let's see. I think it should be 0.005 and 0.995. You know what? This is we need to do something smaller, because with so few observations. Oh, let's just bump this up. Let's do 10,000. Let's see if we can do it. Okay, 10,000. Okay, that wasn't that bad. Okay, cool. So now we have a lot of them, just because with the 99% interval and only 100 observations, doing percentile there is really hard. Okay. Our studio. Okay, there we go. So there is our 99% confidence interval for the probability that someone with a malignant melanoma lives longer than 5 years. Pretty cool. So that's an idea that you can basically, if you have a data set and you have a statistic and you want an interval estimate, boom, Bootstrap. So, there's pluses and minuses of the Bootstrap. The plus is that it just kind of always works. The drawbacks are it's really computationally heavy, and then we're calling this a 99% confidence interval, but it's probably not really a 99% confidence interval. The true level of the interval is probably slightly different. I forget. I forget where I heard this term. I really wish I could cite a source on this, but someone called this brand of statistics rough and ready statistics. Like it always works, it mostly works, and you can kind of just do it. So that's yeah. So that's sort of a quick introduction to the Bootstrap. Again, that's really sort of more of a concept for 428, where you would go into a lot more depth in this. Probably look at some different versions of Bootstrap. But the thing that we're going to be focused on a lot in this course is this idea of creating Bootstrap resamples. Let's go back here. Wait, how do I? Oh. Sorry. Okay. So this idea of creating these Bootstrap resamples is probably going to be the most important concept in this course, because later when we get to random forests, this idea will be sort of in the middle of that method. So we need to know how this works. But again, if you have a data set, up at the top here, and you have a statistic that you're interested in, and you want to say get an interval estimate, Bootstrap, there you go. Okay, so I normally close these videos by saying that I don't know how to stop these videos, and then if you've made it to the end, or if you watch this whole stream, good job.